This lesson we're going to learn about factors and how to factor numbers. The first thing we have to talk about here is the definition of a factor pair. It says 2 is a factor of 10 because 2 times 5 equals 10. 5 is also a factor of 10. The pair 2, 5 is called a factor pair of 10. We look at example 1. It says the brass section of a marching band has 30 members. The band director arranges the brass section in rows. Each row has the same number of members. How many possible arrangements are there? Notice they go through the factor pairs here. I'll write them out as well. We can take 1 times 30 to get to 30. We can take 2 times 15 to get to 30. We can take 3 times 10 to get to 30. 5 times 6, and then you can also say 6 times 5. But those are the same thing. So those are the factor pairs. Again, the pairs are 1 and 30, 2 and 15, 3 and 10, and then 5 and 6 are your pairs. Okay, so what I'll have you guys do is go ahead and pause the video and try these 4 problems. Again, this story problem is very similar to what we just saw for the story problem before. It had 30 members in the band. This is 38 members, so you're going to figure out all the factor pairs of 38. So go ahead and list out all the factor pairs for 1 through 4. Now that you've had an opportunity to try these for 1, we'll go ahead and list them out. We have 1 and 18. We have 2 and 9. We have 3 and 6. And that's all of our factor pairs for 18. For 24, we have 1 and 24. We have 2 and 12. We have 3 and 8. We have 4 and 6. And there's all your factor pairs for 24. Number 3 for 51, this one's kind of tricky. 1 and 51, obviously. The trick for 3 to figure out if it goes in, if my numbers add up to a multiple of 6, then 3 goes in. 3 actually does go in, and it goes in 27 times. And those are your only 4 factors of 51. Okay, the last one here for the members of the woodwinds, we would list them out. Here are possible solutions for how many rows. We have 1 and 38. Let's see, 2 goes into 38. Let's see, 1, 9. Does 4 go in? No. 5, no. 6, no. 7, no. 8, no. 9, no. 10, no. 11, no. 12, no. 13, no. 14, no. I think these are the only possible 1 and 38 or 2 and 19. Pardon my son, he's noisy. Okay, so for prime factorization, they show you the tree method in the book. I never have my students use the tree method because it's very hard to remember the tree method. And if you don't know how to break numbers down, the tree method looks a little bit complex. Really, the way that the book did this right here is something that I like to call the ladder method, and I'll show you it off to the side here as well. So what they did is they broke it down by the biggest or the smallest possible prime. So they started with 2. So we have 60. And we're going to start with a 2 and break it down, and we get 30. Then we keep breaking it down by that factor until we can't anymore. 30 divided by 2 is 15. 2 can't go in. Sorry for all the background noise, guys. 2 can't go in anymore, so I'm going to have to go on to 3. 3 goes into 15 5 times. 3 does not go into that, but 5 does. Once we get a 1 at the bottom, we're done factoring. So when we see the prime factorization of 60, we would put 60's prime factorization is equal to 2 times 2 times 3 times 5. Or, as the book says, that's also equal to 2 squared times 3 times 5. So again, they use the factor trees here. I use the ladder method. It looks similar but not quite the same to these. It says find a factor pair and draw branches. Circle the prime factors as you find them. So again, it's easiest if you just understand that let's take the smallest primes possible and break it down by those numbers. Notice here that what they do to break this down is they have a 4 here in the middle on both. The 4 is not a prime factor, so that does us no good. Okay, so instead what we will do is we will use the ladder method. So again, let's do the ladder method over here. I'll write it out, ladder. We take 48 and we break it down by the prime factors. 2 is a prime. 2 goes in 24 times. 2 goes in again 12 times. 2 goes in again 6 times. 2 goes in again 3 times. And 3 goes in 1 time. So notice here when we write out our prime factorization, we have 48 is equal to all these 2. So I have 1, 2, 3, 4 2's. 2 times 2 times 2 times 2 times 3. Or, same answer as the book here, we can write 2 as a power, 2 to the 4th power times 3. Either one of those answers is just fine. But again, I like the ladder method a little bit better, especially when we go to finding greatest common factors. It helps us out quite a bit. Greatest perfect square problems are actually kind of tricky. We have to find pairs of numbers for perfect squares, or we have to find more than one pair of numbers. So this 1575 thing, when we break it down using the ladder method, you could do that. It would take a little bit more time. Again, we can use a calculator. So 1575, and we would divide it by 3 to start with. Let's see, 3 goes into 15 5 times, 7 2 times, 15. So we get 525 if we divide it by 3. We can divide that by 3 again. It goes in 1 time. Then into 22 it goes in 7 times, and into 15 it goes in 5 times. 3 does not go into 175 again, but 5 does. 5 goes into 17 3 times with a remainder of 2. We get 35. 5 goes in again 7 times, and 7 goes in 1 time. So again, using a calculator is fine, but I just use the ladder method to break this same thing down. Again, here's where I like my my primes. My primes are lumped together here, so you can see that I have 2 3's. That's going to give me a prime factor that goes into a number. So one of my prime factors is 9 because I have 2 3's. Another prime factor that I have is 25 because I have 2 5's. The other ones that are kind of hard to see sometimes are some that we have when we have pairs of multiples. So if I have 2 3's and 2 5's, I can say that 15 times 15, 225 is a perfect square that fits in as well. And if there was another 7, so let's say hypothetically that we had a 7 down here, we could pair that up too. But since we only have 1 7, we can't do that. And we have our greatest common factors with 7 doesn't really factor in because there's only 1 7 and he's all by himself. So really all we can look at are the pair of 3's, the pair of 5's, and then the fact that we can take a pair of each of them out and make them a perfect square in 225 with 15 times 15. All right. So on this page, you guys have your examples. Go ahead and pause the video. Again, please make sure that you pause the video and try these. It does you no good to skip this and just write down the answers. Pause the video, try these next 5. After you're through with these 5, we will have the assignment posted. Okay, so number 5, when we did this, the prime factorization of 20. Again, we're not looking for the factor pairs. Factor pairs is different from prime factorization, so we break it down using the ladder method. For 20, we get our answer 2 squared times 5, or you could have written 2 times 2 times 5. Number 6 with 88, again, we look to use the smallest primes first. We break it down and get 44. We break that down again and get 22. We break it down again and get 11. 11 is a prime number. So for 88, when I break it down, we get 2 to the 3rd times 11. Or you could put 2 times 2 times 2 times 11. Number 7, for 90, we break it down. We can divide by 2, we get 45. We can't divide that by 2, but we can divide it by 3, and we get 15. 15 can be divided by 3 again, and we get 5. 5 can be divided by 5 and we get 1. So my prime factorization of 90 will give me 2 times 3 squared times 5. Number 8, 462. This one's probably going to be a little bit bigger. 462. We can divide that by 2. Sorry, I got to squeeze that in there. It goes in 2, 3, 1. Let's see. 2 does not go into that, but 3 does. 3 goes into 21 7 times with a remainder of 2. So 77 times. Again, if you need a calculator, go ahead. 77, let's see, 5 won't go in, but 7 will. 11 times. 11 goes in 1 time. So this one's kind of a tricky one. 462. Again, if you use your calculator and guess and check, that's fine. But we get 2 times 3 times 7 times 11. Sorry, it won't fit there. So there's 4 factors. None of them are the same. The last one, what is the greatest perfect square that is a factor of 396? Again, remember, for number 9, what it's asking is how many pairs of factors are in there, and are there any double pairs? So let's see. 396, we break it down first. That's what we have to do. 2 goes in. Let's see. 2 goes in 1, 9, and 8. 2 goes in again. Let's see. 9, 9. 2 doesn't go in, but 3 does. 3 goes in 33 times. 3 goes in again 11 times, and 11 is a perfect square, or excuse me, prime. So my factorization for 396 is going to be 2 squared times 3 squared times 11, or we could write that as 2 times 2 times 3 times 3 times 11. So my perfect squares that fit in here, here's one perfect square, 2 times 2, one of my perfect squares is 4. Another perfect square, 3 times 3 is 9. And then finally, notice that I have a perfect square in, there are 2 pairs of 2 and 3 right here. So one of my perfect squares would also be 6 times 6 because I have that pair. So the greatest perfect square that fits into 396 is 36, and you can divide that and check and make sure, but I'm sure that is your answer right there. Here are your other 2, 4 and 9. Okay. This assignment will be posted on your calendar as well, but it's going to be on page 28 and 29. We're going to do 4 through 32 even, 35, and then 40 through 44 all.